Welcome to PhET. This video primer will give you an introduction to the simulation features and uses. This overview is intended for teacher viewing only. Sims are designed to be exploratory tools, and showing this to students can interfere with their exploration of the simulation.
The Neuron simulation is a one-screen sim designed to help your students understand how an action potential is formed in a neuron. The sim shows a model of an axon, including a cross-sectional view. The neuron can be stimulated using the button, causing the cell to depolarize and then repolarize. A legend is provided to help students identify the ions and channels that play key roles in the propagation of an action potential. Students can zoom in on the cross-section, which might help them keep track of changes that occur. In my class, I begin by asking students to describe the features of a resting neuron. Students can select or hide several features to help them accomplish this task. Selecting concentrations displays the concentration of sodium and potassium ions, both inside and outside the cell. Watch what happens to the display when I check charges. Notice the net charges inside and outside the cell are now visible. By default, all ions inside and outside the neuron are shown, including ions far away from the cell membrane. Watch how the display changes when I uncheck all ions, causing only the ions crossing the cell membrane to be shown. Next, I ask students to describe what happens to charge and ion concentration when an action potential is propagated in the neuron. Students can stimulate the neuron and alter the speed of the simulation to see changes that occur when the action potential is generated. Students might notice that the Stimulate Neuron button is inactive until ion concentrations reach levels seen in a resting neuron. This provides an opportunity to discuss the refractory period, enabling students to determine the reasons for this phenomenon. Let's set the sim back to normal speed. Finally, I ask students to determine the sequence of ion channel opening and closing that causes the change in ion concentration and charge across the cell membrane. Let's select Potential Chart to better track these events. Now when we stimulate the neuron, we can see changes in membrane potential over time. It's helpful to pause the simulation and use the buttons to step forward or backward in time, or I can drag the tracer to investigate specific portions of the graph. It's worth noting that students can sometimes struggle with how membrane potential is measured. In this simulation, membrane potential is measured relative to the inside of the cell. To get students to pull this all together, I might have them generate a list of steps that cause the generation of an action potential in a neuron. I ask students to include information about the flow of sodium and potassium ions across the cell membrane, the changes in ion concentration, and the types of ion channels involved. I then ask students to map these events to the potential chart generated in the simulation. Finally, I have students place these events into two categories: events that cause neuron depolarization and events that cause repolarization. This simulation can help your students build a mental model of the events needed to generate an action potential in a neuron, which can give a solid foundation for more complex topics, such as the role of the myelin sheath in action potential propagation.
You can find more resources for using this simulation on the simulation webpage. Teaching ideas and tips for using PhET can be found on our Teacher Resources page. Thank you for being a part of the PhET community. Find more information about PhET on one of our social media pages or by subscribing to our newsletter.